My computer is so tired. No, it just gets tired. Needs a break. Needs a break while I read jobs.
All right, let's go ahead and get started. Welcome to the Lucky Lecture 13, 53, 23, 73, 23, Mobile Sensing, Learning, and Control. Today we are going to talk about exclusively computer vision, which essentially we're going to talk about using OpenCV. A2 grades are up. A3 grades will be up soon when I get to grading them. A4 is going to be due the Friday after spring break, which is approximately 3 weeks away. And just as a reminder, and if you have questions about A4, now would be the time to ask. For Module A, I want you to create a face detection app where you're going to highlight multiple faces in a scene and highlight eyes and mouth position. And for extra credit, if you can display if the user is smiling or blinking and with which eye. And you're going to use the iOS API completely for that. Weird. The Module B is going to be essentially using OpenCV to, and I want you to use OpenCV for Module B, because essentially the idea behind this is that I want you to get some experience with OpenCV on iOS. Even though you can do Module B without using OpenCV. I don't want you to. But essentially, I want you to tell me the heart rate of an individual. It's going to be a course estimate. And the way that I'm going to test that is I'm going to have a pulse oximeter on one hand, and I'm going to have your app on my other finger. And I'm going to see how close the beats per minute are. And it just has to be a course estimate. Okay? What does that mean? Probably plus or minus 5 beats per minute. Question.
I thought about it and you're probably going to get to it anyways. So
Wait, no. What is it? If I get to it, I'll...
So like a course estimate, we do like the 10-second estimate for BPM and then just have like a...
Yes, yeah. Take an estimate over about 10 seconds. 5 seconds is going to be not enough.
Right.
But take an estimate over about 10 seconds and then spit out a reading.
Okay.
Right? And let me know in some way that you're taking a reading and it's not ready yet. You know what I mean? Okay. So, let's get started. Oh, and then optional, display an estimate of the PPG signal. Okay. Everybody know what I talk about when I say PPG from last lecture? Good enough. Okay, so the agenda for today is, let's do OpenCV in iOS. Okay, we're going to look at using OpenCV as a tool, and I'm going to focus on what the outputs of each of these different algorithms are. We're also going to focus on the implementation of that, how to use OpenCV properly in this framework. We're going to ignore most of what's going on under the hood, except to give you an intuition about what the algorithm is, right? So by the end of this lecture, I would expect you to be able to use X, Y, and Z algorithms, but not explain in detail those X, Y, and Z algorithms, okay? Right? Because if we were to do that, that would take an entire semester, right? There are courses that are devoted to computer vision, okay? We're just going to be using them in a mobile context, and that's what this course is about. So, OpenCV and iOS. This was created by Intel a while ago, and then it was open sourced for the open source community to use. It has a lot of different computer vision algorithms that are built into it, sophisticated ones. It's got things that were created in 2012 and are now integrated into the OpenCV framework, right? It's very, very updated, and it's got a large user community. And so it's open source in the best sense of the word, which means it has a really big community behind it, right? Which is the only reason that open source works, right? This is one of those situations where it does, okay? And OpenCV has advanced the state-of-the-art in computer vision by allowing people that don't know a whole lot about the algorithms, that don't know how to program a bunch of things together really, really quickly, to use them, right? And so that's what I want you to get out of this course today, or out of class today. So One thing to keep in mind, OpenCV is made to run on essentially a desktop. It wasn't designed with the mobile platform in mind. However, the framework and the manipulations that have been done to compile OpenCV to work on iOS are really, really good. And that means that it works really fast, right? It's not going to be as fast as the hardware accelerations that you got from Core Image, right? Core Image is Apple created them. They knew the exact hardware that it was going to be running on. OpenCV is as optimized as you can get for C++ code, okay? Right? So it's not going to be able to use all the different hardware accelerations that we got from Core Image. Okay. I am not going to take lecture time to show you how to do OpenCV installation. I will go through the steps really, really quickly, but I'm not going to do it step by step. So today's lecture, I'm going to do it just a bit differently. What I've been doing in the past is, well, I started out the course and I was using code snippets, right? And it was so, bam, like a bunch of stuff got filled in. People didn't like that so much. So I started using where I was typing everything out. People got really bored to tears while I was doing that. So today, I'm going to go back to kind of a hybrid of the code snippet stuff. I've bought a bunch of code already written that I'm going to go through with you. So it's going to be a little bit quicker so that you're not as bored during lecture, and we get to cover a lot more. But to cover it all, we need to go just slightly quick, right? Because this is the last lecture before spring break, which is pretty amazing. Okay, so the overall process is you're going to download the OpenCV framework for iOS. You can download it from here and also have step-by-step instructions, right? This is also posted on the class website. You don't have to just grab it from the slides. You're going to drag that framework into your project, and then you're going to manually add a bunch of different framework dependencies, okay? And OpenCV is C++ code. You're going to have to, wherever you use OpenCV, wherever you declare and instantiate that class, you're going to have to remember to rename your view controller or your model, whichever you're using, to a .mm file. Okay, so essentially, you've got this OpenCV2.framework that I'm essentially, you just grab in and drag onto frameworks right here. And then inside of the your precompiled headers, you'll put this import OpenCV2 OpenCV.hpp, right? And that's essentially for all of your classes that load. It's going to import the OpenCV2 framework. All right, and then you're going to add all of these dependencies that you see here, which I'll let you guys do on your own. Okay, so it's a bunch of stuff right there. It takes 3 minutes. All right, so the tutorial is also going to show you how to set up something for video capture. And you're going to use a delegate protocol, right? So you're going to use the CV video camera, and you're going to use a protocol that says, hey, I am who you're going to send these protocol messages to every time that the video camera updates a new image, right? So it's something we've used in the past. It's very common to use protocols in iOS. It keeps a flat design hierarchy, so we don't have to have multiple inheritance. And it looks like this. You'll have at interface your view controller, CV video camera delegate. You declare yourself as you're going to implement that delegate protocol. And then somewhere in your image, you're going to have an image view and a CV video camera, right? CV video camera is what is from the OpenCV framework, right? I just called it video camera, right? So that's going to be a property of the class. That's going to have you, you're going to be able to get access. This is straight off of the website too. This code is there. Essentially, well, most of it is there. Essentially, what you're going to do is instantiate this video camera with CV video camera, alloc, and init with the parent view. And this is where you're telling it where you want everything to be rendered to. And that's where I give it this self.image view so that it will render inside that image view. And it's going to render very, very quickly. Okay? So you set the delegate up as yourself, and then you can have access to a bunch of different things. So you can set the default device position, right? So that is front or the back. Device position is they're talking about the camera device right there, okay? Whatever. It's bad naming. But anyway, it's camera device. Oh, no, they said capture device position, right? Camera device would be better. The session preset, you can set it to this. I'm going to use 352 by 288. You can use all of the different presets that we had before, right, that we talked about for when you were using the video analgesic. Right, so high, medium, low, you can do all of that. And then you'll give it a frames per second, which probably actually works in their class. It doesn't work in mine. and then a grayscale mode. Set the grayscale mode to no, because that's going to determine what color space you're working in, right? So if you set grayscale mode to no, it's assuming that you're working in BGRA, right? So blue, green, red, and alpha value color space. There's different color spaces that you could work in, right? That it might want to display differently. So if it was an RGB color space or RGBA, everything would be inverted between the blue and the red, right? So basically, grayscale mode, set it to no. If you set it to yes, it'll give you YUV color space, and it won't display properly if you don't do the proper. If you don't display it properly, okay. All right. So there was view did load. The biggest thing that you have access to is this thing called process image, right? And this is something that you have to implement this when you're doing the CV camera delegate protocol. Okay, so this is the method that you would have inside of your view controller. And essentially what's sent in is an image, and it's of type mat. Okay, so OpenCV works with matrices, right? So every image that comes in is a matrix, right? And so it has a blue, green, and a red color plane, or it might have an alpha color plane, right? Too? And those are just matrices that you can do operations on. Is that okay? Right? So this matrix right here is sent in as an image. You'll notice it is passed by reference, right? So any manipulations that you do to that image are going to be returned and displayed out to screen, right? So this gets called once you've captured from the camera and right before rendering, right? So you have access to do anything right here. So essentially what I've done here is I have declared a matte image copy, and I've called this convert color, which is an OpenCV function. So what I'm calling in here is I want it to convert it from BGRA to BGR, right? So that gets rid of the alpha for processing, right? Most of the OpenCV framework is built on the fact that you're going to be working with 3 color planes, BG and R. It doesn't know what to do with alpha, but iOS needs the alpha to be displayed as a screen properly. Okay, so when you're doing the processing, most of the time, the first thing you do is you get rid of the alpha. You do any kind of processing right in between those, and then you do another convert color from image copy back to image, right? Because that's what we want to get sent out. And I'm just going to convert it. Oh, that should be BGR. BGR to BGRA. Okay? Oops. Anyway, does everybody see why this wouldn't work on the convert color? A couple of nods. I'm good with that. All right, moving on. So you are not on the main queue inside of process image. Okay, you're on a separate queue, right? So if you want to update any of the user interface, you need to do that on your own. You need to call get main queue and then dispatch async. Okay. The OpenCV framework is mostly updated for iOS 7. It is not completely updated for iOS 7. Essentially what that means is that some functions that you want to use, some functions that they are using to display out to the screen are deprecated. They still work. Okay, so Apple does a wonderful thing with every release. They deprecate a function, and then somewhere along the lines, it becomes a runtime error to use that function. Okay, so they're using some deprecated functions in here. You're at the mercy of the people that do OpenCV for essentially doing all of that updates. But it's open source, you can implement it yourself. I don't recommend that because you probably won't do it right if you haven't worked with OpenCV a lot in the past, right? It's a big open source community. It will be updated soon, okay? And then when it is, you'll just drag the new OpenCV framework into your project and you're done, okay? Now you can compile from source if you need to, but that framework is basically a binary, right? It's just been cross-compiled for ARM7, okay? Everybody know what I mean when I say that? Good. All right, OpenCV Demo. Let's just jump right in. Okay, so I have created an application. Inside of this application, I have a UI image view, and then I have a picker down here where I can pick a bunch of different operations that I'm going to be doing. We're going to go through each of those operations as we go through the slides on lecture, and I'll show you the code for doing each of those. So this is called CV Master. So the first thing that you'll notice is there's a lot of stuff in here. That image view is essentially right here. Right? I have an outlet to my image view, and here's my view did load, right? So view did load is right here. So I've got a super view did load. And the only thing that you really need to pay attention to is this video camera object, which is of type CV video camera. So this is created using lazy instantiation, and it's essentially all of the operations that you saw before, except the frames per second is set to 24. Okay? So I init this with self.imageView, and then in viewDidAppear, I'm going to call self.videocamera start, and then it's actually going to start doing the processing. The reason that I do this in viewDidAppear is because the OpenCV framework relies on some things to be set up inside the view. If those aren't set up, so if you tried to call this in view_will_appear, some things aren't set up quite yet in the view, and you're going to get some weird behavior. You're going to get weird behavior, right? It may not know the orientation that it's supposed to be in, those kind of things. Okay, so I'm going to do this in viewDidAppear. In viewWillDisappear, self.videocamera.stop. Wow, interesting. Okay, so with only those lines of code, where I'm essentially alloc and initting with the parent view, and then starting and stopping, this will work immediately, right? So let's run this on my phone. See if we get a runtime error, because now we're in class. Okay, good. That is the back of this. Look, it's you guys. It's not me today. Okay, so essentially, here it is. We're running at 24 frames per second. That is you staring back at yourselves. Wonderful. That is the end of this OpenCV demo. Yes, questions? Oh, nice, nice. So essentially, what's going on here, this is running at 24 frames per second. If I go down, what do I want to show? Anything right now? Hold on. Now we'll leave it. Notice all of the frameworks that I have manually added into right here. And notice that OpenCV2 is a framework that's dragged in. Okay? Back to the lecture. And let's stop that from running. And let's come back to me. Upside down me. Don't stream. Okay. Okay, so before we get too far, I do want to show you guys how to access the torch, which is essentially the flash on the camera. Okay, so with the 5S, there are two different torches that are on it. One is for color balancing, one is for white balancing, right? So they've essentially got one that's very, very white LED, another one that is a yellow LED. You only have access, as of current right now, to one of those LEDs that you can turn on and off, and that's the torch. Okay, the functionality of the other color balancing one, you don't have control over right now. I'm assuming they will expose that soon. Okay, it's not exposed right now because it's only available on the 5S. So if you want to turn that off, then essentially this is the way to do it. You get a handle to the AV capture device, so audio video capture device. And then this is the same way that it was done in the video analgesic, is that default device with media type, AV media type video. So I'm going to get an access to the video device. If I have a torch, right? Maybe I'm running on the iPad. I don't think the iPad has a flash. I could be wrong. But if I have a torch, what I'm going to do is I'm going to lock the device for configuration, and I'm going to set the torch mode to either on or off, depending on this on-off bool variable that was sent in right here. So the way that I implemented this in this class was I created a toggle torch button that essentially every time you hit the button, it turns the torch on or off and then updates that using the set torch. Okay? Cool. So if you wanted to do that with the camera, if you wanted to do that when the user is getting their heart rate, you can. That is a really good question. My hunch is yes, that it does, because it's using automatic reference counting, and it probably has a timeout for locking the configuration. That may not be true if your view controller is .mm, which is C++. I haven't tested it. Always lock it. If you don't, I mean, don't do that, right? Don't forget to to basically unlock the configuration, right? Okay, good. So we talked about before, your input is a matrix. That matrix, the way that is saved in memory is the data is interleaved blue, green, and red. That means, so this color conversion, CVBGRA to BGR, essentially gets rid of the 4th byte in that array that it sends back to you, right? So your image is a giant array that is the number of rows times the number of columns, and the first byte is the blue channel in the very top left pixel, and then the green, and then the red. Okay? After that, it goes over to the next pixel in the row. Okay? So you have to get a pointer in the array for the row and the column. The way that you do that in iOS is you do image.pointer, and then you give it the row and the column where you want the pointer to. Okay? So what you can do here starts from the upper left and goes row by row this way. So essentially what you can do here is I could say for int I equals 0 to 50, I could say image.pointer at I, and then I could get the blue, the green, and the red channels that way if I wanted to. Okay? It's a little bit slow, but you could access it that way, right? And it really is just a pointer. Right? So one of the things I could do here is I could say, okay, this is an unsigned char, a pointer to that, and then I could say point at 0, 1, and 2 and access it this way. I could get a pointer to the very upper left point in the image and cycle through the whole thing as quickly as possible just by incrementing that pointer, which would be the right way to do this, the fastest way to do this. Right? So I can access this unsigned char point in any of the ways that you can imagine with C++. This accesses one pixel. This accesses the pixel that's directly to the right of it, unless you're on the end of the row, in which case it goes to the next column. Sorry, the next row, first column. Any questions on how that data is interleaved? No. Good. You probably won't run into issues until you run into issues with it, and then you come back and look at these. Okay. Oh yeah, so that's the pixel at I. That's the next pixel in the row. Wonderful. Okay, so with OpenCV, a lot of times one of the things that you're working on is you don't need the full resolution of the image. And so you want to do some fast image downsizing. Okay, so for reducing the image size quickly, one of the things you can do is just get rid of every other pixel, right? And that essentially takes your image from here to here. Right, this, so it's a quarter of the size if you get rid of every other pixel this way and that way, right? So every other column, every other row. That's called nearest neighbor. Essentially, you take the nearest neighbor and you throw it away. There's no interpolation or anything that happens right there, right? So it's an integer that you want to downsample at. The problem with that is this. If you take an image and you just throw away every other row and every other column, there's a lot of high frequencies in that image. Okay? So essentially this brick pattern, that's a very spatially a high frequency, right? So you get alias signals that are kind of like, you see these high frequency sine waves that are showing up inside of that? The way that you would get rid of that is take your image, blur it, then downsample. Okay? So you blur it, and then you can get an image that looks like this. If you use the OpenCV function, which is peer down, pyramid downsampling, you can essentially give it the image copy and save it into image, and you will get something that's a lot more like this, right? So let me blow these up. Essentially, that high frequency aliasing is gone now, right? Good. So if you need the processing power, you need to downsample so that you can do some processing on this giant image that's coming in, use CV peer down. Okay, some other OpenCV operations. You can do filtering. So the way that filtering is done is you actually get a matrix that's a filter. All right, so if I have a mat, I'm going to get a Gaussian filter right here. I'll do CV get Gaussian kernel. Remember, a kernel is just a filter. This is saying I want it to be 25 pixels by 25 pixels, square, and I want the standard deviation of that Gaussian that's in the middle of it to be 3. Okay? If you want to run that, I'm going to go CV filter 2D. On my image copy is the input. Here's the output. Just put in -1 right there. You'll almost never have to put anything right there. And then I'm going to put in the Gaussian filter that I want it to convolve with the image, right? I could also do this using a Gaussian blur, image copy, and then I give it a size. But this one actually allows me to have different standard deviations in the X and the Y direction. Okay? And size doesn't have to be symmetric. All right? If you're running a filter that has symmetry this way, essentially where the column and the row are identical to one another, then you can run that filter much more efficiently across your image. Because you can distill it down to an operation where you're just convolving with each row and then each column, rather than convolving the whole filter that you have.
So for processing, it would be better maybe to crop the image to make it a perfect square matrix first.
No. What do you mean?
Well, you could crop it to make it a perfect square.
The image?
Yeah.
Yeah, but I mean, the way that it's doing this is actually through convolution. It's not taking a 2D FFT. So like the kernel size would still be, as long as that's square,
Oh, okay.
then it's probably separable. Do you know what I mean?
Yeah.
So if you want to do inversion, you could do a bitwise not operation, right? So I'm going to take image copy to another image copy right here. You can do statistics. Let's say I wanted the average pixel density across the image. I can do a scalar. This is a CV scalar, by the way. OpenCV, it's a data type. And then average pixel intensity equals CV mean of image copy. What that's going to return is a scalar, and for each color plane, right? So if I had given this with a BGR image, then oh, come on. If I had given this with a BGR image, the value at 0 would be the mean blue on the blue channel. The value at the 1 would be the mean on the green, the mean on the red. Okay? If this was BGRA, there would be a fourth value right here, which is essentially the average alpha value on the channel, right? So that function might be useful. At this point, I've given you everything you need to do A4. Okay? All right. Does anybody not see that? All right. There's also this thing called color conversion that you can do, and there's lots of different operations that you might be able to do with the color conversion. We'll talk a little bit more about color conversion as it comes up, but essentially, here's the convert color object where you can take one image to another, and there's a lot of different things that are built in. You can take it to different color spaces, and we'll talk about why you might want to do that. All right, so let's actually show those basic operations happening. We'll pull this down. Okay, so the first thing you'll notice is all of that code that I had done before for turning on the torch and off the torch is included in here. You have access to it if you want to. And then I have this picker view that I'm doing, and I've declared myself as the delegate and the data source for this picker view. And essentially what happens there is I have all of these CV example types, which is an NS array that I'm using to populate that picker view. Right? A picker view is just something you can scroll through. Right? It's got all the little wheel of things. Right? So you can get the raw video, which is what we just looked at, right? Or some of these things that we just talked about, right? So if I want to average the pixels, just raw access the pixels that are there, or do a color inversion, which is that bitwise not. Okay? So if I look down here, inside of my process image function, right? Where did I get the process image function? Quick quiz. He's like yawning through my quiz. What? It's from the delegate. It's from the protocol, CV camera delegate, right? It's from the CV camera delegate, right? So the image gets sent in here, and I'm going to declare the image copy, my gray frame, and output, which I might use in some of the processing that's there. And essentially, if the case equals 1, I've got my color inverter. So I'm going to convert color from image to image copy. I'm just going to get rid of the alpha channel, do a bitwise not, right? Save the result in image copy, and then convert it back. Whoa. Man, I copied that over everywhere. From BGR to BGRA. Okay? Excellent. I wonder how many times that shows up in the code. Okay, so let's go ahead. Oh, wait. So that's the color inverter. Here, I'm accessing the pixels, right? So int ij, I'm actually using a slow method where I get the pointer at ij, and then I set the value equal to full blue, 0 green, full red. Okay? So this is a byte. It's 8 bits that you get back for each pixel and each color, right? So 0 to 255. Okay? I'm going to go from I and j equals 0 to counter, so essentially I'm going to have a square. And I'm going to set these values equal, right? So I've got this, which is, I don't know, some color. And then this should be blue. Okay? There it is, BGR to BGRA. Finally fixed it somewhere. And I'm going to convert the color, and I'm going to increment the counter. If counter is ever greater than 200, I'll set it back to 0. So I'm just going to keep doing this, setting pixels. Case 3, average pixel intensity. Wow, there's some new code here. Let's see what's going on here. Wasn't in the slides. So I'm going to do that color conversion. You guys have that. I'm not going to talk about it. So now we have a scalar, which is my average pixel intensity. And I'm going to get the mean of my image copy. Then I'm actually going to put text up onto the image, right? And the text is going to be the average of my blue, green, and red channel. All right? I'm going to call this function, so I call sprintf and just store the value of that into text, right? And remember, we're working in C++ now. This is not an NS string. It's actually just a char array, all right? So I'm going to save the values for average pixel intensity .val at the 0, 1, and 2. And then I'm going to call CV put text, where I'm going to take this text, put it in this image at this point. Right? So it's going to go 10 pixels down, 20 here, and it's going to throw that text onto the screen. Okay? You have a very limited supply of the fonts that you can use with OpenCV. Okay? I'm using CV Hershey Plain. You have like 4 more that you can use. All right? And then everything else is related to the color, the line width, all of that stuff. You can look it up if you're interested in it. Okay? All right, so if that's the case, we're going to go ahead and do that. So let's run this and see what that looks like. And we're going to use you guys. So I've got a little icon down here in the bottom right corner. It's wonderful. I can turn the torch on. Yeah, I can turn it off too, because everyone's looking. All right, so I'm running at 24 frames a second. Let's do this color inverter. See what that looks like. Here's you guys on the color inversion. That's just a bitwise operation. Okay. We can go over to that access pixels, which looks like this. Oh, here it goes. So it's going to go, it's incrementing that counter. I'm just setting all of the pixels. Apparently I chose pink. Is that pink or purple? Oh, it looks pretty pink on my phone. Pretty pink. Anyway. And then you'll see that the very right-hand side of that is blue because I was accessing the pixel right next to that pointer as well, just to show you that you could do that. Okay? Normally, you don't want to go through pixel by pixel in a for loop and try to set these pixels manually. You can if you need to. OpenCV exposes that. You don't want to do, you want to use built-in functions that are in the C++ framework on OpenCV when you can. They're faster. Okay? And then we can average those pixels together like this and display them up at the top. Look at that. So the average for blue, now let's look Oh, interesting. All right, so let's see what happens if I put my finger over it. Oh, everything turns black, essentially. Red is still going. Oh, I'm going to turn the flash on and see what happens here. Let's see what happens. Wow, the red channel and the channels are fluctuating still a little bit. You can see the red channel is very, very high to 255. Okay? But it is fluctuating a little bit. You see it fluctuating? The mean value? My hands must be cold. It usually fluctuates about a little more than that. That's my heart rate. Okay?
You just haven't been drinking enough.
I just haven't. You know, I wonder if coffee is a vasoconstrictor. I've had a lot of coffee today. All right, I got kids. What are you going to do? Okay. Okay, so there it is. Wonderful. Those are the first 3 operations that we could do. What was the other one? Change the hue. We'll get to that. Hey, there they are. Webcam. All right. Come on, seriously.
Can you see the camera for that? Like, what's that IP address?
Oh, this is an app that I downloaded that I'm going to write my own when I get time. Actually do it. It's just a webcam app. I could stream it to that IP address if I wanted to. But I keep turning that off because I don't really want to. Okay. Yeah, that's cute. All right, so that was the basic operations OpenCV demo. How are we doing? 406. We are awesome. Okay, color conversion. So to display properly, we wanted to use BGRA, right? So this is BGRA to BGR, BGR to BGRA. Pretty simple. I'm just taking and adding the alpha channel. Who cares? All right. So I can also do some other interesting operations. For instance, maybe I want to convert color, and I've got image. I'm going to convert it from BGRA to gray, right? So essentially, I'm going from 4 channels down to 1 matrix, 1 channel, which is grayscale, right? And then if I want to, when I want to display that, I can't save image as just a grayscale. I can't save it out because when I save that into my image view, it is expecting it to be BGRA. So I have to convert it from gray to BGRA, right? So if I do that, what it's going to do is convert it over into image copy. In image, right here, when I go over from image copy to image, this was a grayscale image, then it converts over into this. That's still going to look grayscale, it's just all the colors are filled in so that it can display it properly. Is that okay? It's still going to be grayscale. I can also do some other interesting operations, such as hue, saturation, and value. Okay, has everybody ever heard of HSV before? What is HSV?
I've seen it on like color picking websites. Like, use this one instead.
You want to use HSV, hue, saturation, and value, when you're manipulating color. And we'll talk about why that is. But essentially, it's one operation. You can convert this over from BGRA, or you know what? I don't know if that exists. I'll show it to you. But essentially, you want to convert it from BGRA over to this hue, saturation, and value plane. And then you want to convert it back, or else it's going to look really funny when you try to display it. Okay? So essentially, with HSV, here's RGB. So if you were to take 1 pixel, and I was going to graph out its blue, green, and red values, I could do that on a plane, right? And so wherever that pixel landed, that's a specific color that we can interpret. Okay? So this right here is called a color cube. White is right here at the very edge, right? That's 255, 255, 255. Black is 000. It's on the other end. Okay? And all of the colors are in between. Right? So I could plot each pixel inside of a color cube. Everybody okay with that? The problem with that's not very intuitive. What color is 187, 236, 56? No clue. Right? That is not the way that your mind interprets color. That is not the way that people interpret color. Wouldn't it be great if we could convert this over to somewhere where I had a specific value and that value corresponded to a color? Right? Instead of these 3 things that I have to interpret. Well, that's where this hue, saturation, and value comes in. Right? So instead of plotting each pixel inside of a color cube, I'm going to have a color cylinder. And this color cylinder the way that I can go into it is looking at essentially the very top of it is polar form, right? So here's the very top of it right here, very top of this cylinder. The value of the hue tells me what angle I am at on this cylinder. Does that make sense? All right, so if I'm at this angle right here, I know I'm going to be red. If I'm at this angle right here, I know I'm going to be blue. Right? And same thing with yellow, right? So each angle tells me the color that it's at, that is there. The saturation tells me how far out on the cylinder I am, so how colorful I am, right? Because even though I might be the same shade of red, I can be the same shade of red, but I can kind of control how much of that red is actually displaying through, right? So essentially it kind of tells you how much white and black is also embedded inside of that same hue, right? How colorful I am. Value tells me the raw intensity, right? So how dark and how light is this pixel, right? So value and saturation are very, very interrelated to one another, right? They're very correlated. This hue component is not so correlated to the rest of them because it just tells you what color you're at. Another thing, that hue component, when it's very, very white or very, very black, that hue component is tough to measure, right? Because what is that color when it's really dark or really white? We don't know. Okay? So let's talk a little bit more. So let's say I have an original image, looks like this. If I were to convert that over to grayscale, it would look like this. Okay? Can everybody see that? Yeah, look. Okay, so on the projector, I've got reds, I've got greens. Okay, so if I were to look at the red, green, and blue components of this color image, and I would just look at each of those as a grayscale image, this is what I would get, right? So this is the red component. You can see it has very high values where red is, as you might imagine. Here's the green component. Here's the blue component. The blue component has very high values where you see blue. Notice how the green component here looks very, very, very similar to the grayscale image. Everybody see that? That is because your eye is most sensitive to green for detecting illumination. Why? What?
Well, it has to do with the level of the ocean that most fish were in. For the reason we have eyes that can see color spectrum. Whole different thing.
Yes. Yes. So we're going to talk about like the evolution of the eye and how that was created. Absolutely. Another thing that you can look at it if you want to look at pure just sensing, then you have essentially 3 different color receptors inside of your eye, right? You've got blue, green, red. Okay? This green component overlaps with both the blue and the red sensors that are inside of your eye for color. Okay? So that green component is actually really, really sensitive to just lights and darks because it's sensitive to almost your entire wavelength of light that comes in. That's why grayscale and green are very, very similar to one another. And there's evolutionary arguments about why that is. Right? Good ones. Well-founded ones. Okay, so let's take this over to HSV. What we perceive as color. Right? So hue, the value, the richness, and the intensity. So here's what this looks like in HSV space when I convert this over. So essentially, here's the original image. You'll notice every single distinct color on the hue plane has a distinct value, right? So all of the reds are a low value. The blues are a little bit about, they're higher. They're more white. Everything else is kind of between a red and a blue, right? So the value of that tells you the color that's in the image. Is that okay? The saturation is telling you how colorful those parts of the image are. And I think it's pretty easy to see this is the most colorful, the most saturated part of the image, right? Which we can kind of see right there, right? The value, coming back right here, is essentially telling us the lights and the darks. It's really, really related to the saturation right there. And if you want to get the color value, if you want to get the intensity, you need to kind of look at saturation and value together. Okay, and that essentially will give you a grayscale image if you were to kind of look at these and combine them. Okay, that's also done for you if you look at hue, saturation, intensity, HSI space, slightly different than HSV space. Instead of a cylinder right here, you essentially have a conical that goes like this, where the correlations between saturation and value have been taken into account. You can also look at LAB color space. You can look at YUV, YCBCR. There's lots of different color spaces. All of them are very, very related to HSV, and some of them are better than others for kind of corresponding with what people perceive as color. All right? The best one you can probably do is LAB. Let's wait on edge detection. Let's do this. Let's go over here and do some color conversion in our OpenCV app. Okay, so I'm going to change the hue inside of an image. All right, so here's how you would do a conversion over to HSV. The way that I did it was CV BGRA to BGR, BGR to HSV. The reason that I did that is because this alpha component, there is no BGRA to HSV using OpenCV. Okay, so there's a little bit of a processing delay that we have to worry about right there. The next thing I'm going to do is, so now image copy, the three planes that are inside of image copy are hue, saturation, value. All right? So the first thing that I'm going to do is I'm going to split those, because right now those are interleaved, right? It's HSV, HSV, right? So essentially what I'm going to do is I'm going to copy those over to layers right here. So layers is going to have three different values, right? So layers at the 0 is the hue plane. It converts it over to a matrix where all of that is the hue plane. Layers at the 1 would be saturation and then value. Okay? What I can do here is I'm going to call this function CV add. And I'm going to add on this hue adjustment amount. I think I made it 80, right? So hue right here, it's from 0 to 255. I'm going to add on this, and I'm going to save it inside layers at the 0, right? So all I've done is add a bunch of stuff circularly, right? So if I add above 255, it's going to go back up this way to layers. And then I'm just going to merge those again and save it into image copy. Right, so now I've taken that and I've put it back into the language that OpenCV understands. And then I do a color conversion. What is this going to do? I'm changing the hue component. I'm not changing the saturation. I'm not changing the value. All I'm changing is the hue of the image, the color. No, I'm asking you a question. What is it going to do?
Rotate around that wheel.
It's going to rotate that wheel. So colors that showed up one way should show up as a different color. But they should look very realistic because I haven't changed the intensity or saturations or anything that's there. It should just be a different color, but be photoreal. Okay? So let's try it. Let's see what it does. I don't know. Maybe it doesn't. Maybe it'll crash. Come on. Let's go bigger. There's you guys. You've got a red shirt on. So let's see what happens when we adjust the hue of your shirt. So now you've got a green shirt on.
Why are we all blue gray now?
No, your skin tones. Your skin tones have been adjusted. And this is like a Walking Dead app now. All right? So it's good.
This orange shirt looks awesome.
Is this how the color lines of other apps work? By adjusting
It would look better in
Say that again. What's the what?
that, like they have color blindness simulating.
Yes. So essentially what you could do here is, this would be a great project too. You can transfer the hue of anything that's red and pull it over to green, and you could see the world, what it would look like if you were red-green colorblind. So you can take that hue and just kind of like take out the red and kind of squish it into the green, and that would tell you, right? This is a blue marker right here. Wonderful, right? I'll prove it to you. It's blue. All right, so you can do some fun things here. All right, hue adjust. That was hue, saturation, and value, right? So what does that tell you? If you switch things over to HSV space, That is a much better place to work in when you're working with color. All right?
Dude, I want orange jeans instead of blue jeans. That's mine. I prefer the world in your phone to the real world.
Fair enough. All right, let's open up this app. There I am again. Hey, look. And we'll make myself a little smaller. How are we doing on time? We're good. We're going to get through this whole thing. It's going to be awesome. Okay. Voila. Edge detection. All right, so we're probably going to want to do some edge detection in the class, right? Well, maybe. You don't have to do it for the assignment. But one way or another, when you use an OpenCV, edge detection is always something that comes up. I want you to know how it works and what to do with it. Okay, so essentially, we talked about edge detection a little bit last time, right? Where if you want to get the gradient, you can use the gradient to find out where an edge occurs in an image, right? And so we actually used those Sobel edge detectors, right? Which was essentially, it was a filter that looked like this, right? And a filter that looked like this. So this is going to be sensitive to all of the vertical edges. This is sensitive to all the horizontal edges, right? Okay, so now let's do this. Instead of running that across the image that I have right there, right? This is just going to take the difference between two pixels, like pixels, right? We'll take the difference on that edge line. Let's say that I have an image, and that image, I'm just going to pull out one row of pixels and plot them. Okay, so this is the value of those pixels in grayscale, and this is which pixel I've chose, right? So the image was 2,000 pixels, it's a big image, 2,000 rows. This is the value of what those pixels look like when they're graphed. They're kind of noisy, right? So if I were to take the gradient of that, where I take this pixel, multiply current pixel by 0, and subtract off the last pixel. If I do that, that's the derivative, right? That's d by dx. This is what I get. Where's the edge? I mean, it is right here. You can kind of see it has a higher value, but all of those noise pixels, those have a huge derivative on them, right? Like they're jumping around. How do I fix that? Average. I'm going to smooth it. All right? How am I going to smooth it? I'm going to use a Gaussian filter. Okay? What? Yeah? Okay. The beauty about a Gaussian filter is that you will never get ringing. Ringing. Like this. Like if you use some other filters, you can filter them across an image, and you'll get artifacts in the image where you get like sine waves that weren't there before. Right? If you use a Gaussian filter with a big enough kernel size, essentially the Fourier transform of a Gaussian filter is another Gaussian filter. So you'll always be multiplying in frequency by something that's smooth. You'll never be multiplying by something in frequency that's ringing like this, right? So essentially, I'm going to take this Gaussian filter, I'm going to run it along this, and here's the output. So if I convolve that with this, I get this nice kind of thing right here. And now, if I take my d by dx, I run my Sobel edge detectors, this is what the gradient output looks like, right? There's the edge. Night and day difference, right? Awesome. If I wanted to, I could look at curvature, right? So what is curvature? Mathematically, what's curvature? If I was going to define curvature by a mathematical operation that was related to derivatives, what would it be? The second derivative, right? So it's my concavity. Absolutely. So this right here, that's the essentially second derivative. What I've got here. This is kind of known as the Laplacian of a Gaussian. LOG. So if you ever see a log filter, it's the Laplacian of the Gaussian. Okay? It just means it's the second derivative of a smoothed kernel. Essentially, I could run this across my image, and anywhere where I have an edge, I'll get a zero crossing, which is what you'd expect from the second derivative. You get a zero crossing, that's a change in concavity, right? You get an edge. Okay, so let's take these filters and let's run them across an image. So here's what it looks like. So if I run those Sobel edge detectors and then essentially take the absolute value of both of them, I'm going to take this image, and if I run them across them, I'll get this, right? Where you can see it's pretty good. Like anywhere where I have a really hard, distinct edge, I get something right here, right? So this would be gradient edge detection. It works pretty well. Does anybody know the story behind this image?
I've seen it like 100 times.
This image shows up everywhere in image processing. It's in almost every single paper. This image was originally, the reason this story is interesting is because this image actually came from a Playboy article. All right? Someone used it in one of the very, very first image processing papers. They were like, oh, here, you know, this is called the Lena image. They used it. The problem with it, this was copyrighted photography. And essentially, it was used so rampantly everywhere that that magazine, they just released the copyright. They were like, well, whatever. That's fine. We'll just release the copyright to it. But anytime you look up an image processing paper, you've probably a 95% chance you will see this image as one of the things that gets processed inside of it. Okay?
She had no idea what she was getting into.
No, she was flattered by the whole thing. Like they did a big like thing. This is from the 70s, essentially. And so she was like 90 years old, and they came back and they were like, yeah, hey, what do you think of this? And she was like, that's great. Never thought that my modeling career would go off that way. Anyway, that's not what I'm supporting. I'm talking about why this is interesting. Okay, let's go. Can we do better than this?
Yes.
We can always do better.
How can we do better? How can I do better using this gradient image as a starting point? What if I want to know where an edge is? Huh? What?
Curve interpolation.
Yeah, you can do curve interpolation. We're not going to do that, though. But it's good. Thank you for answering. Okay, one of the things we could do, I mean, like, what if I want this line right here? I don't want this giant, like, that's a lot of pixels that are white right there. You know what I mean? They're showing me where the edge is. I want one line. How could I get one line across that? Like no, I just want one line. I want to know exactly where that edge occurs. Where does that edge occur from the gradient? In the middle. Keep it going. What if I could check the local maximum? What if I could say, oh, it's a local max right here. And right where that local max occurs, that's where that edge occurs, right? You're going to be dumbfounded by how many times you come back to finding local maxima inside of an image or a signal. It is just, you're going to come back to it 1,000 times. So let's check local maxima. We're going to use something, we're actually going to go even more than that. We're going to do something called canny edge detection. So a canny edge detector works like this. We're going to get the local maxima of the gradient, right? We're going to find out where all of those local maxima occur. And we're going to say, okay, the local maxima that, let's see if they're above a threshold. If they're above a threshold, I'm going to say those local maxima are the edges. The next thing I'm going to do is, for all of those things that are above, like that, let's say it's a high threshold. I only want really strong edges with that first threshold. Then I'm going to go back, I'm going to say, wherever that gradient occurred, let me look perpendicular to that local maxima. I'm going to look along that line, essentially, right, which is perpendicular to the gradient. That's along the line where it occurs. And I'm going to have a lower threshold. And I'm going to say anything that's above that lower threshold but is on the same kind of line perpendicularly, I'm going to say that's an edge. Okay? So essentially what that does is I've got my gradient image right here. I'm going to say, okay, here's a really, really strong edge right there. It's very, very white. Let me go perpendicular to that edge. I'm going to search in either direction, and I'm going to have a lower threshold. And anything above that lower threshold in those directions, I will say is an edge. All right? That's called hysteresis thresholding. It just means you've got two different thresholds. It's above one, then there's a lower one that might, if it meets other criteria, I can get to. So if I do that, I'm going to get a canny edge detector. It looks like that. Okay? Cool? Okay. If you want to do this in OpenCV, you're going to convert the color over to grayscale. I used RGB again. Whatever. Then I'm going to call this function called canny. And it's going to do everything that I just said for me. Excellent. It's going to do the local maxima. I don't even have to find local maxima. You guys should be like jumping up and down right now. No? Okay. So I'm going to give it these two thresholds. The first threshold is this is the lower threshold and the higher threshold. I also need to give it the kernel size for my gradient. The gradient, it's usually 3 by 3 that we do. But you could do a larger and larger gradient. Okay? The one thing it doesn't, oh, look at that. I actually put those in there. The one thing it doesn't do is smoothing. Right? So if you want to use this, you might do some smoothing right beforehand. You could run a Gaussian filter and blur the whole thing and then do canny edge detection. Okay? But maybe edge detection isn't just enough. I don't want to know it's just an edge there. I want to know if that edge is part of an object. I want to know if that's a contour. Right? So how might I do that? I want to go from edges to contours. Well, the way that I'm going to do that is through a connected component search. Right? So essentially I've got these zeros and ones that are in here. Right? Very easy to see. No? Let's make them a little easier to see. Okay, so essentially I'm just going to do connected component search. I'm going to come across, I'm going to start at the top left, and when I come to a pixel that's binary, right, I send it to the canny edge detector so I get zeros and ones out. Edge, no edge. When I find the one that is an edge, I'm going to do a connected component search along all of that. Right? I'm just going to look in 8 directions and see, is there another 1, value of 1, binary, next to it? If there is, bam, that's part of the same thing. Okay, so that's a connected component. Oh, cool. It's the first letter of my name. I made this, so I get to do that. And then I can do that with every single blob that I have in the image. The next thing I can do, if I want the contour of that, let's say, well, I can just take any one that has a 0 around it. Okay? And that'll give me the contour. Right? So now I've gone from having an edge to now I can have a contour along these things, right? So this might be an object that I'm interested in. So let's see what that looks like. So we'll go, let's bring this down. Okay. So there's some thresholding in the image. You can look at that if you want. Blurring, canny edge detector. Here we go. Okay, so here's my canny edge detector, which is essentially everything that I just gave you before, except I actually fixed it here, for converting the colors over to gray. Grayscale, canny edge detection right here. I'm not doing any smoothing, so there's probably going to be a lot of false positives. Okay? I've also done a contour detection. Right? So essentially, I do canny edge detection, and then I call this function called find contours. And I'm going to give it the output for my canny edge detector. I'm going to give it this contours and hierarchy variable so it can save where the contours are in my image. And then I'm going to draw them onto the image. And the way that I'm do that, the first thing I'm going to do is what I can do is I can get the bounding rectangle for that contour, right? Which essentially is just here's a square that completely encapsulates that entire contour. Or if I go down here, I did the same exact thing right here, contour detection, all the way up to when I draw it. Here I'm going to get a color, and then I'm going to actually just draw the contour straight onto the image with a random color right here. Oh, that's going to look great. Should we do it? Let's do it.
What's contours?
So the contour is the outline of anything.
What's it held in? Is it a matrix?
It's, okay, so contour right here is a vector of points. Okay, so essentially one contour would be a vector of points, right? Right, x, y, z coordinates that I want to go through. It's another vector of that, essentially because I can have a vector of for each contour, right? All right, so let's run it. See what it does. All right, so let's go up here. Let's do there's some thresholding if you want to do thresholding. You guys can look at that code if you want. We can do blurring, canny edge detection. There you are. What if I want the bounds of each contour? Well, I can do the contour bounds. Oh,
What?
there you guys are. I could do it to my laptop screen here. Oh, look at that. Maybe I just want to do the contours themselves. Just a random color on each contour. Bow, 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 bow.
Wow.
You can make your own live music video. This is running on a phone. Are you kidding me? Come on.
What is that music video that's stylized like that?
I have no idea.
Take on me, yes.
That's from my generation. You got to be careful. All right. Yeah, whatever. Okay, so we're good. All right, so we'll stop that. I'll put you down right here. Webcam it. Blah, blah, blah. It'll eventually do its thing. I have to wait till it flips or else it's going to resize on me. Come on. Extra credit for anybody who writes me a better video camera app. That's not true, by the way. But it would be really cool if you did. Okay. How we doing on time? 15 minutes. Oh, we're good. We're good. Okay, so remember how we talked about face detection last time, right? And we talked about these wavelets that were called Haar wavelet filters. They were just zeros and ones that I'm multiplying by the image and adding things up inside of those rectangles. And then I go in and I choose the best rectangles of running across the image. I put them through a classifier. I put those classifiers into another classifier. And I take those classifiers and I cascade them. That's called a Haar cascade. Okay? You can build your own generic Haar cascade filter with OpenCV. Okay? And you can train it on whatever you want. Or you can go out onto the internet and you can download trained Haar classifiers. Okay? So the only thing that you need to do is load in a trained classifier into OpenCV. So you can get some trained XML files. Here's a start. If you go to this website right here, there's a bunch of different Haar classifiers that you can use for detecting objects inside of an image. Okay? You can also train your own. It's not trivial to do that. The data collection to train your own classifier is pretty horrendous. You can do it, but you have to get a bunch of examples and a bunch of negative examples of something that you want to find and classify in an image. Okay? So what I did was I went out and I found one that was already trained for me. There's lots of them out there. They're trained, the way that that classifier is written, it's just an XML format that I can load in from OpenCV. And the way that I do that, is I'm going to create this OpenCV object called CV Cascade Classifier. I'm going to name it Classifier. And then what I'll do inside iOS is I will drag in that XML into my bundle, the app bundle, and I will get a handle to it using NS main bundle, path for resource. Oh, a Haar cascade frontal face underscore alt2. Whatever, that's what they named it. It's of type XML. And then the classifier, I'm going to convert that file name over to a string because that's what OpenCV understands. It doesn't understand NS string, right? So I'll convert that over to a string. So now that classifier is loaded up. All the parameters, it's good to go. If I want to run that classifier, I can create this vector of objects, which are rectangles, for wherever that object was recognized. And I can say classifier.detect multiscale. Run my classifier at a bunch of different scales. On my gray frame, save any objects that you find inside this, and then I'm going to take them and display them out onto the screen. Okay? There's a bunch of different things. You can find stuff trained for faces, trained for eyes, noses, trained for iPhones, different XML formats. People just have a lot of detection algorithms out there. You can go train your own if you want to. So what I've done, inside of my supporting files, I have a bunch. Here's 4 different XML files. If I were to open each of those up, it takes a little while to load because they're ASCII text. Don't know why they did that. Should be binary. but essentially it gives you the structure of a classifier and a bunch of trained weights for each of those. So essentially what we talked about before, except everything's open source, everything's exposed for that entire classifier. So now if I want to run these, well, the first thing that I did, where's viewDidLoad? I took it out of viewDidLoad. Essentially what happens here is in my picker view, every time I load up a different picker view, if I get to different values in it, I'm going to load up, so I'm going to have different file names for different HAR cascade classifiers. And they're all trained for face detection. They're just slightly different training examples for each. They're all for front faces. And you can download those from here. So I'm going to do that. I'm going to say self.classifier equals whatever I put, inside the file path. Okay? And you can look at that code. If it's confusing at all, you can look at it and see what it looks like on your own time, if you want to. Okay, so first thing I'm going to do is switch the camera. Oh, look, it's me. Okay, so I just hit that little camera button down there. Okay, so let's go down here. HAR cascade. So this is the default implementation right here. There's some false positives, but it is detecting my face. Let me load up a different classifier. This one's based on a tree. My frame rate has gone way, way down. It's taken a little while to run these, but it is finding my face. I wonder, can it find you guys? Hey, there it is. Let's try another one. How about this one? Oh, that one's pretty good. What about Alt 2? Oh, that one's pretty good too. Mark, how we doing? Hey, I got him. Carly? Okay. So essentially, you can now go out, train your own if you want to, grab a bunch of XML trained classifiers and run them locally on the phone in real time with a video, image, and track anything that you want. Okay? Well, we're not done yet. I got 9 minutes left. Keep trying to click on stuff. I'll just do it this way. Here, it's better. Look at that. Okay. The solution to the problem was not to place my phone in that orientation. Okay. So that was the user-trained HAR cascades that you can just drag into your app bundle and load up. Wonderful. All right. I would be remiss, Matt's already laughing. I would be remiss if I didn't talk about the Hoff transform. I call it Hoff because I'm a country boy from Oklahoma. I think it's actually called the Hue transform or something. He's French. Okay? But we'll talk about the Hoff transform. The Hoff transform is generically, you can use it to find any shape inside of an image. Okay? The way the Hoff transform works is you do edge detection. For each detected point, for each edge that you find, you draw a shape. So if we're looking for circles, I'm going to draw a circle with its center right on the edge that I have. And then every time I encounter another edge, I'm going to draw that circle again in the image, and I'm going to just add it in to the image. This isn't coming up. And then I'm going to check for local maxima. Essentially, let's say that I had an image. Can you guys see that? Let's say I had an image right here. There's a circle that's right here, okay? Let's say there's a circle. Maybe it's not a perfect circle. It looks like this, right? That's something. I'm going to do edge detection, and I'm going to assume that I find most of the edges on that circle, right? Maybe it's like this. I find an edge here. I get a little bit of that one there. What I'm going to do is I'm going to take a circle that's of the same radius of this one. And every time, I'm just going to run across this. And every time I find an edge, I'm going to draw that circle. When I find another edge, right here. I'm going to draw that circle again. But now, what I'm going to do is add it into my image, right? So my image started off as zeros. When I found that circle, I drew the circle. So all of those had a value of 1. Then I'm going to, when I find it again, this point right here where they overlap, that would have a value of 2. I'm just accumulating the circles that are there, right? And you can see the same thing in this. So here are some quarters, right? And essentially what I'm going to do, I've run some edge detection, and then I'm going to take a radius that's the same size of a quarter, and I'm going to run, or same size as a penny, and I'm going to run it across there. And what you can see is wherever, as I'm drawing these, they all converge right on the center of where that circle is. So if I go through that, find a local max inside of my image, bam, there's the center of one of the circles. I have to do that for every circle of a different radius inside of the image. Okay, but it's a very fast operation because I'm working with binary images, right? So I look for maxima inside of this x, y, and for each radius. I look for local maxima that's inside there. If I want to use that, I can call this function called off circles. And I'm going to say, here's my image, save the circles into this. Hoff gradient's the only thing that's supported. This has been this way for like a decade now, and they've never updated this. You can only use CV Hoff gradient. And essentially, I'm going to say, okay, here's the distance between the centers of the minimum distance between the centers of the different circles that can be there. Speeds up my processing. And I'm going to say, here's the canny edge detection threshold, the upper threshold that I want to use. And then this 40 right here, that's the threshold that I'm going to use for the local maxima, right? You're going to only be able to get this by, essentially, this local maxima that occurs, say, right over here with a penny, that has to be above 40 accumulations across it. You'll have to mess around with that parameter, okay? It's an art, not a science, defining what that parameter value is. Okay, and then I can do min-max centers. If I enter 0, it says I don't know what the minimum and maximum radius is that my circle might be. Okay? So we'll do the OpenCV demo, call it the Hoff. Basically, have fun with OpenCV. I'll do the demo here in just a second. Because it's a powerful framework. It has lots and lots of contributors out there. The only problem with it is that each of the algorithms, they might be implemented in a slightly different way. And it's because it is open source and there's not a whole lot of control over the way that things get implemented, right? So it's however the author wrote their C++ code, and hopefully they did it in a manner that kind of meshes well with OpenCV, but you may have to learn their specific semantics on how to use that code, okay? However, there's lots of examples. It's a huge user community. Have fun with it. When you guys get back from spring break, we're going to talk about microcontroller basics. We're going to start getting into Bluetooth. This is going to conclude our mobile sensing computer vision lecture. All right, so let's end this on Hoff circles. All right, so the way that I did this, the first thing I did was reduce the noise. So I actually did do some Gaussian blurring in this. All right, so I converted over to grayscale, blur it, allocate this circles variable, which is a vector of floats right here that it comes back with. Essentially, it is the XY center and the radius of each circle, right? So it's a vector of length 3, X, Y, radius. Then I'm going to take those circles, I'm going to draw them. I'm going to draw the outline of the circle, and I'm going to draw the center of the circle right here. And you guys can look up that code for how that actually works. All right, so let's go over here to off circles. What? Oh, come on.
Oh, wow.
Very fast. You guys get to see my coffee. All right, it's pretty good. Oh. Having a little trouble with that one. Probably need to adjust some of my thresholds.
It's a size thing too, right?
It's a size thing too. We're done. I don't get like applause for this lecture. This is my open. Look at that. Yeah, now we're talking. Massage the ego. Okay. If you guys got any questions, it's lab time right now. Don't wait till after spring break to start assignment 4. Don't do it. You will be in a world of hurt. Okay? There's a lot to do with module A and B, and you got 3 weeks. 3 weeks. Spring break doesn't count.
We don't have
We don't have the max and if you're out of town for the entire spring break.
Wait, you guys don't have access to this room?
Well, but
Yeah, we're gonna
You're going to the Bahamas? Yeah, I feel bad for you.
Wait, no, I have
You guys are going to the Bahamas. What did you spring break? What does this do? It's a good thing you can do this in 2 weeks.